This OpenVAS scan report reveals the massive footprint of unpatched CVEs active in an enterprise environment. Notice the density of the high-severity red bars and the 10.0 ratings. Drilling down into a specific critical finding shows exactly what that exposure looks like: a backdoor payload successfully answering on the network, granting instant root access. Automated scanners effortlessly find and exploit legacy network protocols. These mechanisms were originally designed for trusted local networks, leaving them severely exposed in modern, hostile environments. Remote Procedure Call, or RPC, is a primary example. It is an inter-process communication mechanism that allows a program running on one host to execute code on a remote host. Because early versions of RPC lacked strict input bounds, it became a major attack vector. The configure worm serves as the historical baseline for how attackers weaponize this flaw to achieve arbitrary remote code execution. However, focusing solely on patching network protocols ignores the foundational flaws in the underlying operating system architecture. Legacy inter-process tools built for implicit trust will always function as gateways for automated exploits if the host machine itself lacks structural defense. We must look past the network traffic and drill down directly into the physical and logical storage layer of the server. The legacy file allocation table, or FAT architecture, is inherently flawed in a multi-user environment. It operates as a completely flat directory. Its critical vulnerability is a total lack of file-level permissions. Any authenticated user can access, modify, or execute any file. The non-negotiable first step in server hardening is migrating to the New Technology File System, or NTFS. This architecture strictly enforces access control lists to block unauthorized users from restricted directories. Once local files are secured, administrators have to manage how those files are shared across the network, which introduces older protocols like server message block and the Common Internet File System. CIFS operates to share network resources, utilizing either broad share-level security or much stricter user-level security modes. Because early iterations of these sharing protocols contained numerous vulnerabilities, modern architectures lock down backward compatibility holes by forcing the network to use updated versions, like SMB 3.1.1. A perfectly secured network protocol is entirely useless if the local file system it connects to lacks access control. Enterprise security must be stacked vertically. Moving up the OSI stack, the next structural failure point is the application layer, specifically regarding default enterprise software installations. Legacy Microsoft SQL Server deployments are prime examples, as their default configurations frequently left production databases critically exposed. The most devastating vulnerability was the automatic creation of a system administrator account with a blank password. Discovering this granted an attacker instant remote admin access to the entire database. Early Internet Information Services, or IIS, installations were similarly vulnerable out of the box, requiring network administrators to run explicit lockdown wizards just to secure the basic web server. Applications in C and C++ present memory corruption risks. This diagram represents a temporary buffer. Lacking input bounds checking, if input exceeds allocated space, excess data spills into adjacent memory, overwriting the return address. This buffer overflow allows the attacker to execute arbitrary shellcode. Relying on default software configurations or trusting unvalidated code inputs allows attackers to bypass all external perimeter defenses. These application vulnerabilities must be actively mitigated at the identity management level, which is handled by the domain controller. Administrators have to enforce a hardened password policy. This requires quarterly age limits, a minimum length of 8 characters, and high-complexity rules that forbid dictionary words. It also requires configuring strict account lockout thresholds and lockout durations. These specific settings mathematically neutralize automated brute force attacks. Mixed enterprise networks require Linux servers to communicate with Windows architectures. Administrators deploy Samba, an open-source CIFS implementation, to trick Windows into seeing Linux resources as native files. Bridging these systems radically expands the attack surface, blending the unpatched vulnerabilities of both ecosystems. This combined attack surface makes manual patching architectures impossible at an enterprise scale. This matrix compares two distinct update paths. Windows Software Update Services, used primarily for local patch publishing, against System Center Configuration Manager. SCCM deploys a suite of tools to manage scheduling, server deployments, and patch functionality across complex global domains simultaneously. In heterogeneous networks, automated centralized patch management is the only viable strategy to outpace the constant discovery of new vulnerabilities. Shifting focus to active defensive protocols requires locking down local machine settings before an attacker establishes a foothold. Administrators must disable local guest and administrator accounts entirely and strip out all default hidden shares from the system. At the network perimeter, this interface shows the absolute requirement for edge filtering. Perimeter routers must drop traffic attempting to hit TCP and UDP ports 137 through 139, as well as port 445. Blocking these specific NetBIOS and SMB ports is the primary mechanism to kill external null session attacks, preventing anonymous users from enumerating network shares. However, technical perimeter defense completely fails against social engineering. Aggressive user awareness training is necessary to stop employees from handing over credentials. Because perimeters are eventually breached, internal post-exploitation monitoring, specifically log review, becomes the ultimate failsafe. Running standard commands like ipconfig/all, netstat-r, netview, and gpresult might be benign individually, but executed sequentially, they are a massive red flag, indicating an attacker actively enumerating the internal network. Internal logging and telemetry prove that perimeter breaches are inevitable, and threats must be actively hunted inside the network. When defensive telemetry is ignored or missed, attackers deploy their final payloads. They install Trojan programs to establish hidden file servers, upload arbitrary code, or drop keyloggers to continuously steal passwords. But a standard Trojan payload operates entirely differently than the severe threat of a rootkit. A rootkit bypasses the standard application and user spaces entirely, embedding itself directly into the kernel level of the operating system. This kernel-level access allows the rootkit to manipulate the OS itself, hiding its own binary footprint from standard security scans and vulnerability queries. Once a rootkit establishes deep persistence, standard mitigation fails. It often requires a total system wipe and complete remediation to clear the network. Enterprise security is a continuous, adversarial process of architectural hardening against legacy debt. It is never a default state to be set and forgotten.